Hi, today I'm going to walk you through a goodness of fit test. So our goodness of fit test is similar to our test for homogeneity, except for instead of seeing if all the categories are the same, we want to see if they match an expected ratio. So the example says a biologist conducted an experiment with randomly selected rabbits, each of which was heterozygous dominant with respect to fur. Capital B is brown fur, lowercase b is white fur, capital C is straight hair, and lowercase c is curly hair. The biologist knew that results should be in a 9:3 to 3:1 ratio. Below are her observed results. So currently we have the counted number of rabbits. So if we add this all up, it should add up to 32 rabbits altogether. And now to figure out my expected. So if I take the expected ratio 9:3:1 and I find the sum, I get a sum of 16. So that means for the brown straight hair, if I have 9 out of 16, I can multiply 9/16 by 32, so I would expect 18. Likewise, we would expect 6 white straight, 6 brown curly, and 2 white curly. Now, we want to determine, is there sufficient evidence to say that the distribution of rabbits matches the theoretical results? Test at the 10% significance level. And remember, this 10% significance level is just our alpha. So we're saying that alpha equals 0.10. So step 1 is to add up the row total. We already did that with 32. Step 2 is to calculate the expected number of rabbits. So I put all of those in. And again, just to remind you, so for example, white straight, we know that it should be 3 out of 16, so we would take 3/16 times the 32. And that's how I got each of those expected number. I'm going to go ahead and pause the video for a minute and write in my H0 and HA. Okay, so the following set of hypotheses can be used for most goodness of fit tests. You just want to make sure to add in some context related to the situation for each one. So for example, my null hypothesis was the observed genetic distribution matches the expected ratio. And then for my alternative hypothesis, it would be the observed genetic distribution does not match the expected ratio. Now, one thing to kind of shorthand this, because it is a lot of writing, is you can use the 2 sets of quotation marks just to say that we're basically copying that first part of the statement before. Okay, again, I'm going to pause so that I write in my assumptions or conditions. Okay, so we still have 3 conditions. So the first one being counted data. Well, because it was the number of rabbits, it is considered counts. The second one being random and independent sample. Now, in this example, it was not stated if the sample is gathered randomly. So I must assume that it is a random and independent sample. And then my last condition is the expected cells have to be greater than or equal to 5. This is not met. Because we only expected 2 white curly rabbits, it would not be greater than or equal to 5. So in this case, if the expected cell counts are not greater than or equal to 5, then you can combine categories. So for example, I've already kind of started below. So because my 2 lowest categories were the brown curly and the white curly, I decided to just combine those 2 for one category for curly hair rabbits. So then I would set up my data. I still have 14 brown straight, 8 white straight, and then I combined the brown and white curly for a total of 10. I'm going to do the same thing for my expected, so 18, 6, 8. Okay, so now for our actual mechanics. So again, if you do not already, you should have out your calculator and your pink sheet as well. So we're using the same formula that we did from the previous test. So the sum of the observed minus the expected squared divided by the expected. So I'm going to pause the video for a minute to write out my 3 components, and then we'll talk a little bit more. Okay, so with only 3 categories, you would be expected to write out each of the 3 components. So for each one, I took the observed minus the expected squared and divided by the expected. And when I add those all up, I get 2.056. Remember with your calculators, so if you go to alpha y equals n/d, numerator, denominator, you can actually type in the fraction exactly as you see it. So this is extremely helpful when doing these types of problems. So now for my conclusion. So the degrees of freedom is equal to the number of categories minus 1. So since I had 3 categories minus 1, I have 2 degrees of freedom. We're going to write our conclusion a little bit different this time. Since the last one we practiced using the p-value, this time I want to practice using the critical value. So I want to look up the chi-squared critical value for 2 degrees of freedom. So if I go to my pink sheet on the very back page, you should see this table. So kind of like we did for the student T table for means, I'm going to look for a tail probability at the very top. So I find 0.1 for 10% significance level, and then 2 degrees of freedom. So my critical value in this case is 4.61. So chi-squared crit with 2 degrees of freedom is 4.61. So my curve, remember, it's always going to be skewed to the right. So if my actual test statistic was 2.056, and my chi-squared critical value is 4.61, since my test statistic was less extreme than my critical value, I am going to fail to reject in this case. So I'm going to pause the video, just take a minute to write out my conclusion, and then we'll talk about it. Okay, so my conclusion is, with a chi-squared test statistic less than the chi-squared crit, so 2.056 is less than 4.61, I fail to reject H0. I have no reason to believe the observed genetic distribution does not match the expected ratio. Now, you could also do this with a p-value as well, and I just want to remind you how you can do a test in your calculator. So I'm going to open my calculator up, go to Stat, Edit. In L1, I put the observed data. In L2, I put the expected data. So now we go back to Stat, over to Test. So I'm going to actually arrow up because I want to get to the bottom here. So I'm looking for chi-squared goodness of fit test. And remember, this one also works for our chi-squared homogeneity test as well. So observed L1, expected L2. In this case, I have 2 degrees of freedom. So here it gives me a chi-squared test statistic of 2.22, a p-value of 0.033, and then 2 degrees of freedom. So again, if I use the p-value because it's less than 0.10, I would fail to reject in that case as well. Now, I'm going to ask you to go on to the next page, try completing that on your own, and then I'll have another video to walk you through that.